Hello everyone, welcome back to our YouTube channel Gurmantra Shiksha Ka Granth. I am your educator Nidhi Dua and I teach you chemistry at this platform. This is our GATE syllabus and topics that we have covered till now are these topics, and without any further delay we are going to study about electron geometry. So basically electron geometry is the arrangement of electrons or atoms around a central atom. But before understanding the concept of electron geometry, let's recall about geometry. So basically geometry is the arrangement of any atom, any electron, any molecule in the free space. And there are two kinds of geometry present in nature. Number one is electron geometry and number two is your molecular geometry. So basically electron geometry is the arrangement of electrons or atoms around a central atom in the 3D space, three-dimensional space, while molecular geometry is the three-dimensional arrangement of the atom that constitutes a molecule. And this molecular geometry gives molecule a particular shape and certain angles. If lone pair of electrons are not bonded to other atoms, means if free lone pairs are present in a particular molecule, this will change the molecular geometry but not the electronic geometry of any atom, any element. If all the electron groups are bonded with no lone pairs, then the electron geometry and molecular geometry are same. These 2 points are really very important. You have to remember these 2 points. Next topic is valence shell electron pair repulsion theory, that is also known as VSEPRT. VSEPRT was given by Nyholm and Gillespie. Valence shell electron pair repulsion theory or VSEPR theory is a model used in chemistry to predict the geometry of individual molecules from number of electron pairs surrounding their central atom. This theory tells about shape and bond angle. Shape and bond angle of any atom of any element is determined according to VSEPRT. The premise of VSEPR theory is that valence electron pairs surround an atom tends to repel each other and will therefore adopt an arrangement that minimizes this repulsion. This in turn decreases the molecule's energy and increases its stability, which determines the molecular geometry. Gillespie has emphasized that electron-electron repulsion due to Pauli's exclusion principle is more important in determining molecular geometry than electrostatic repulsion. So basically, two types of electron pairs are present in valence shell. Number one is bonded pairs and number two is lone pairs. Due to the repulsion between electron pair of valence shell, the shape of molecule and bond angle may be differentiated from electronic geometry. VSEPR theory is based on the observable electron density rather than the mathematical wave functions. VSEPR has a physical basis in quantum chemical topology methods such as ELF and quantum theory of electrons of atoms in molecules. So now we are going to study about the position of lone pairs and multiple bonds. In this particular slide we are going to study about the position of lone pair. In case of particular hybridization, as you have seen in the previous video, the hybridizations, there are 6 types of hybridization present in nature. Number 1, sp, sp2 or sp3. If you have lone pair, in case of sp, sp2 and sp3 hybridization, you can simply locate them anywhere. while drawing the structure of any element, any compound. In sp3d hybridization state, position of lone pair should be at equatorial position. In case third, sp3d2, position of lone pair must be anywhere. While sp3d3, if lone pair is equals to 1, then the position of lone pair will be equatorial position, and if the lone pair is equals to 2, then the position of lone pair will be at axial position. Next is bond length. This is very important because many times a question have been asked about the bond length of axial bond length or equatorial bond length. In case of sp3 hybridized state, axial bond length is more than equatorial bond length, while in case of sp3d3, this becomes opposite. Equatorial bond length is more than axial bond length if the side atoms are same. You have to remember these 2 points because these 2 points are really very important. Now, VSEPRT, valence shell electron pair repulsion theories, important points are: if central atom possesses only bonded pair of electron, if central atom has only bonded pair of electrons, it do not have lone pair of electrons with identical atoms, then shape of the compound will be symmetrical, according to the scientists Sidgwick and Pauling. For example, in case of BF3, the bond angle is 120 degree and the shape is triangular. You can simply calculate the shape by the hybridization, and in case of CH4 and CO2, the bond angle is 109 degree, 28 minutes and 180 degree, and shape will be tetrahedral and linear. If central atom possesses bonded pair of electrons as well as lone pair of electrons, means if central atom in a particular molecule, in a particular element, has both type of electron pairs, bonded pair of electrons as well as lone pair of electrons, then shape of molecule will be unsymmetrical. That is, original bond angle will be disturbed due to repulsion between lone pair of electrons. Similarly, on having different type of side atoms, molecules become unsymmetrical. If element has different side atoms, it do not consist of similar type of atoms, then the molecule becomes unsymmetrical because unequal force will act on the central atom, and this will create a repulsion between electrons. And order of repulsion is lone pair is greater than lone pair bond pair, then greater than bond pair. This is very important because question have been asked from this statement directly. You have to simply calculate the order of repulsion. You have to simply turn this order of repulsion. And this point makes your numerical aspect, that is, if bond angle is increasing, then number of lone pair of electrons should be decreasing, or bond angle is inversely proportional to the number of lone pair of electrons. Means if number of lone pair of electrons increases, then bond angle must decreases. Next point is, if number of lone pairs increases, then bond angle decreases approx by 2.5 degree or simply by 2 degree. As you can see in this following example, and all of the elements hybridization is sp3 hybridized, while bond angle decreases as you move from CH4 to H2O because number of lone pair is increasing. In a different molecule, if central atom have same number of lone pair of electron, means it has constant lone pair of electrons, then bond angle will depend on the electronegativities of two atoms. For example, in case of ABX type of molecule, if side atom are same, as you can see here in this particular example, central atoms are different, oxygen and sulfur, while the side atoms are similar, hydrogen, hydrogen, hydrogen and hydrogen. Then the bond angle will increases if the electronegativity on central atom increases. Now, as you know, in case of oxygen, electronegativity is more than sulfur. If electronegativity of oxygen is greater than sulfur and the number of the side atoms are same, then electronegativity is directly proportional to the bond angle. So basically, the element, the central atom which has more electronegativity will have the greater bond angle, as you can see in this particular question. Another example you can take is for NH3, PH3 and ASH3. Next point is, in ABX type of molecule, if central atom are same and electronegativity of side atom increases, then bond angle decreases. Now you have this similar kind of central atom while bonded atoms are different. In that particular case, electronegativity is inversely proportional to the bond angle. As you can see here, central atom is same, that is oxygen, while bonded atoms are different, chlorine and fluorine. Central atom has the electronegativity. If electronegativity of side atom increases, then bond angle decreases. Because you know fluorine has the highest greater electronegativity than chlorine, that's why its bond angle is minimum for fluorine. Next you have the types of hybridization and possible structures. You have learned about the hybridization in the previous video, and in this video you are going to learn about the shape of the particular hybridization state. Now here I would like to suggest you, please make a personal note for these next two slides, this slide and the next slide, and you have to learn the number of bond pair, number of lone pair and the shape according to the number of bond and lone pairs. You do not need to remember the examples, because you will simply calculate the hybridization state for the example. Type 1 hybridization as your sp hybridization, where number of bond pair are 2 and number of lone pair are 0. In that case, the shape will be linear. For example, in case of CO2, CS2 and BeCl2. In case of sp2 hybridization, if number of bond pair are 3 and number of lone pair are 0, then shape will be trigonal planar. And for the rest of the following, you can simply learn these shapes and number of bond pair and number of lone pairs. These two slides are really very important, because in particular chemical bonding, the maximum chances of being asked the question comes from these two slides. So simply I repeat, you have to learn the number of bond pair, lone pairs in a particular hybridization, and you have to learn the shape for these hybridization states. Next is, you have seen the different kinds of shapes in the hybridization state. If linear, V-shape, T-shape, square planar, pentagonal, pyramidal, trigonal planar structures are present, then these are known as your planar structure. Planar structure means all the above structures are present in a same plane, and remaining structures are non-planar structures. In next point, if someone asks you about the nature of pi bonding with oxygen, if any element you have been given and question have been asked about the nature of pi bonding with oxygen, then you have to calculate the hybridization of central atom. If you calculate the hybridization of central atom and this comes out to be sp hybridized, sp2 hybridized or sp3, sp3d, sp3d2, then the nature of pi bonding follows according to this table. In case of sp hybridization, maximum 2 p pi and p pi bonds are present, while in case of sp2 hybridization, maximum 1 p pi and p pi bond is present, while in case of sp3, sp3d, sp3d2 hybridization of central atom, only p pi and d pi bonding is present. You have to learn this table, you have to learn this point, because this is very important, because this is your direct aspect to ask question, to ask numerical problem. For example, identify the nature of pi bonding. You have given a element NO2. First of all, you need to calculate the number of lone pairs, number of bond pairs in case of NO2. When you calculate the number of lone pair, bond pair, you will get to know about the hybridization state. That is, for NO2 the hybridization state is sp2. And when you remember this point, this star point, you will get to know in case of sp2 hybridization state, maximum 1 p pi and p pi bonding is present with oxygen. So here maximum 1 p pi and p pi bonding is present. Next, in case of XeO4, that is, when you calculate the hybridization state, you will get to know the hybridization state is sp3d2. Now in case of sp3d2, maximum 1 p pi d pi bonding is present. That's why it have been written here, only p pi and d pi bonding is present. Now I hope you all are cleared about the nature of pi bonding with oxygen. Now here is one simple question, you have to simply solve it. Now I would like to suggest you, please pause your video and solve this question quickly. You have 1 minute. Okay guys, so let's start to solve this question. Question is, write down the correct increasing order of the following according to their bond angle. You have to tell the bond angle sequence for this particular series. So the series is SF2, SCl2 and SBr2. Now as you know, in case of ABX type of molecule, if central atom are same, you can see this central atom sulfur is same and the side atoms are different, then electronegativity of side atom depends on the bond angle. If electronegativity of side atom increases, then the bond angle will decreases. So as you know, fluorine has the maximum electronegativity, so the bond angle of SF2 should be minimum, while Br2 has the minimum electronegativity as compared to fluorine, as compared to chlorine, then it must have the greater bond angle. So the correct sequence should be like this. SF2 should have the least bond angle while it has the most electronegativity element, fluorine, while SBr2 should have the greater bond angle. Now I hope you all are cleared about the electron geometry and VSEPRT theory. Let's recall the VSEPR theory quickly. So what we have studied in this video lecture in the previous slides, number 1 point was, if central atom possesses only bonded pair of electrons with identical atom, then the shape of compound will be symmetrical. Number 2 point was, if central atom possesses bonded pair of electron as well as lone pair of electron, then the shape of molecule will be unsymmetrical. If you increases the number of lone pair of electron, then bond pair of electron decreases by 2.5 degree. In a particular ABX type of molecule, if side atoms are same, then electronegativity of side atom increases and the bond angle increases, because in that particular case electronegativity is directly proportional to the bond angle. In next point, you have learned that in ABX type of molecule, if central atom are same and electronegativity of side atom increases, then the bond angle decreases, and each lone pair decreases by the bond angle of 2.5 degree. Now I hope you all are cleared about the VSEPR theory, valence shell electron pair repulsion theory. Now, in case if you are new here at our YouTube channel Gurmantra Shiksha Ka Granth, you can do like, share and subscribe to our channel. You can also join our Telegram channel for new updates regarding to your upcoming exams. You will get free PDF and notes over here. You can also join our Facebook page. For further queries, you can mail us on tanejanehaofficial@gmail.com, or you can also contact us on the given number.